The first thing I want to do is talk about the test. We have our test next week. That's going to cover chapters 1 through 5. That will not cover tonight's material, just 1 through 5. Um, so a few things about the test. You're allowed one 3 by 5 inch card of notes that you're allowed to bring. You can put it on both sides and write whatever you want on there. So if you have a particular problem that you're stuck on or whatever, you can put that on there. Oops, just messed that up. Hold on a second here. I'm trying to get you a tables and formula sheets. The tables and formula sheet are also allowed, and I'm going to put that in the chat here as soon as I get my stuff together here. Let's see. Okay, so there's the tables and formula sheets. You can use those on the test. There's a few formulas on there that will be helpful, but not too much. Will help a little bit. I also have a practice version of the test. Yeah, Caleb, I would print that. Yes. There's also a practice version of the test on MyStatLab. The practice version is much longer than what you'll see when you take the actual test. But if you do have a problem on there, on the practice test that you're unfamiliar with, it's a pretty good chance it's going to be on the real test. So I would, ask me or, make sure you can figure those out before that. I got a question about, can we write in the formula sheets? No, let's keep any writing on the index card. Okay. Let's see what else. StatCrunch is allowed. Scrap paper is allowed. So forth. Now the way we can do this, there's a couple different options. We're going to go to Canvas and then Smarter Proctoring. I'm writing this in the chat. So we go Canvas and Smarter Proctoring, and that'll give you a bunch of different options on methods to take the test. You can take it in one of the FSCJ testing centers for free. You just have to make sure you make an appointment. That can be at any of the campuses. And they have all the information for those. And then another option is doing it online using an online proctor. And the fees vary from about $3 to $25, depending on which one you choose. That's the last time I actually checked the prices. It may have gone up a little bit, but about that cost. So that's up to you. If you want to use the online proctor and pay a little bit, you can do that. If you want to go to one of the campuses and do it that way, that's fine as well. As far as class next week, we're just going to be taking the test, so I'm not going to schedule a meeting next week. If you do want to meet with me, I certainly will, make time to do that. There are different prices, and do I know the different prices? Different services offer a little bit slightly different security measures depending on how much it's monitored. Is it taped, or is there somebody live there watching it? I get a tape, view of each test is taking that way. So as far as the price difference on your end, makes no difference. I would go with a cheaper one. So it's just a little bit different information that's given to me. Okay, I think that's all for as far as the test is concerned. Does anybody have any questions as far as the test is concerned before I look at this week's material?
Yes. It's iCoin, by the way. Is it any, because I live in Vegas and I know my last class that I had, we had to do proctor's test. She sent me a form that I had to have with the signatures of, I guess, the testing department, so that I could take a test out here in one of these proctoring facilities. Is it possible that you could send me that, or how does it go with you?
So you're not interested in doing the online option?
So I have an iPad and they said it's not compatible.
Okay. I haven't done this in a long time, this situation. I'm sure it's easy. I'm not remembering how to do it. It's been a while. If you could send me an email, just saying, hey, I'm in, you said Vegas, I think you said?
Correct.
Yeah, if you could just send me an email and just say, "Hey, I'm in Vegas. What can I do?" I can figure that out and get back to you, tomorrow or the next day and figure that out.
Okay.
Okay. Caleb also says looks like $4 to $8. Sorry, $4 to $11. So we're not talking too much for the online proctoring. Okay, so thank you, Caleb, on that. Okay.
Yeah, also, they have the external proctoring too. Like I'm here in an hour south of Los Angeles, and the colleges around here will let you go take it at a nearby college as well. So for I forget who it was with the iPad, you can do it at a college nearby because they're all affiliated, and they'll let you come take the test there.
Okay.
That actually sounds pretty good. The fact that I haven't done this in a while probably means that there's a reason why I haven't done it in a while. I used to have to do it all the time. And I remember being kind of a pain in the butt on my end. But I don't think it's that bad now. I would try, a good idea is just try to go on Smart Proctoring and see if you can look up a testing center close to where you are. If that doesn't work, then email me and we'll figure out a plan.
Alrighty, gotcha. Thank you.
Okay. That's probably why I haven't done it in a while. I'm sure somebody's told me along the way, but I don't remember. Okay. All right. Any other questions? Okay. So let's look at chapter 6.
Oh,
Again,
also,
this
I
is,
was
go ahead.
gonna ask real quick, do you mind posting the lecture that we did in the chapter 5?
Oh, did I forget to do that?
There's like a question I had asked in there, and I went and looked for it, but it's still the old lecture.
Okay. Okay. I will, I must have forgot to do that. I will do that and I'll do chapter 5 and 6, either tonight or tomorrow morning. Thank you for pointing that out.
Thank you, I appreciate it.
Okay. I just have to remember. Okay. All right. I will do that. Okay, so let's look at this chapter 6. Okay, the chapter 6. What we did in chapter 5, we were looking at discrete probability distributions and more specifically the binomial distribution. And in discrete distributions, there's only a fixed number of outcomes. Like we were looking at exactly 0 successes or exactly 1 success or 2 or whatever it may have been. But now we're switching to more of a continuous random variable. And what we have there is a range of values that the outcome can be. So what we're going to do is we're going to talk about a probability density function, and we're going to look at a uniform distribution to kind of explain how that works. The uniform distribution is the most simple case of this. And then we're going to go into the normal distribution and spend the rest of the day on the normal distribution, get familiar on how to find different probabilities. Okay. All right. So a couple things about a probability density function. That's just a graph of a continuous random variable. Okay, so we have a graph here at the bottom of a uniform distribution between 0 and 10. Okay. This is a key. The total area under the curve is 1. And then every point on the curve has a height greater than or equal to 0. So let's talk about this uniform distribution, kind of explain what this is, how it works, and so forth. So this is a continuous random variable, and the values are spread out equally over the range. So in this case, we have a range from 0 to 10. Every value between 0 and 10 is equally likely to occur. It doesn't have to be 0 or 1 or 2. Any value there, whether it's 2.765 or 3.58624, every value in there is equally likely to occur. Okay. So what we do is we find a range of values, and and figure out Can you guys hear me now? You guys?
Yes, now we can hear you.
Okay, sorry. This is 100% on my end. My internet is going a little crazy. So sorry about that. Let me see if we can try that again. Okay. So if I don't know exactly where I lost you, but we'll do our best to figure this out. Okay. So now let's look at this uniform distribution. Let me try picking up where I left off. So we have a width of 10 because we have values in between 0 and 10. And what I did is I chose this height to be 1/10 so that the area would force to be 1. Okay, so anytime we have a width of 10, I'd make a height of 1/10. If my width was 100, I would make the height 100 so the area is equal to 1. Okay, so what I'm doing is I'm forcing the area and the probability to be one and the same. So let's see how that works in this next problem. So it says refer to the continuous uniform distribution where wait times are uniformly distributed between 0 and 5 minutes. Assuming the pattern is randomly selected, find the probability that the wait time is within the given range. Okay, so in this case, we have these wait times between 0 and 5. Okay. So as soon as we have between 0 and 5, we know our height has to be 1/5. Okay, that gives us the total area under the curve to be 1. Okay, or in this case, a rectangle. Now, what we're looking for in this particular problem, in this number 3, it says find the probability of greater than 3 minutes. So we're trying to find this shaded region here of more than 3 minutes.
Hi, Professor. I'm not sure if you can hear me, but we keep losing you, so.
Okay, we back on? Can you guys hear me now or no?
We can hear you.
Okay, all right. Let's. I'm going to try this one more time. If this continues to happen, we'll just push this lecture to next week. But, I think we might have been lost here right again. I think we're all right. So if we continue this, we'll just push this lecture to next week. But I'm going to do the best I can, and I'd like to get it done tonight. But if we can't, we can't. So sorry for my issue. I believe it's my internet that's causing the problems for whatever reason. Okay, so anyways, when we're doing these uniform distributions, we always find the area, and the area is equal to probability. So in this case, we're trying to find greater than 3 minutes. So from 3 to 5 is our width of 2, and we multiply by the height is 1/5. 2 times 1/5 is 2/5 or 40%. So that's 40% of the area, and that's also our probability of 40%. Okay, or 0.40. So what we're trying to learn from that is that the area and the probability are one and the same. Now let's see what happens when we look at the standard normal distribution. And this is where the heart of the chapter. So we're going to spend a lot of time on this normal distribution and make sure we understand this. And if you guys have any questions, let me know. I don't think this is particularly hard, but it is very important for not only this chapter, but future chapters. So if you do have questions, please speak up, and I want to make sure all those are answered. Okay. So the first thing we see is we're dealing with a standard normal distribution. Now, as soon as we say standard normal distribution, that just means we have a mean of a 0 and a standard deviation of 1. So anytime we see standard, just means mean of 0, standard deviation of 1. Okay. Now, just like the uniform distribution, the total area under the curve is equal to 1. Okay, so the area, again, the area and the probability are one and the same. All right, now let's go down to this problem and see what they're asking and then figure out what we can do. Now, let me just review real quickly here. Remember we talked about the normal distribution a few times, and we have our mean right down the center. And within one standard deviation of the mean, we had 68%, or roughly 68%. Within two standard deviations of the mean, we had approximately 95%, that within two, and then within three is 99.7. Do you guys recall that? That was an empirical rule. We're going to build on that. And we're not just going to be talking between 1, 2, and 3 standard deviations. We're going to talk about much more depth and get any probability one, whether it's greater than a certain value or less than a certain value or between two values. We're going to use that same idea of the empirical rule, but we're going to be much more exact than we were before. Okay. So in this case, it says assume the standard normal distribution, find the probability of the following, and in this case we're looking for less than negative 0.19. Okay. So the first thing we have is that this is a standard normal, so our mean is right down the center, and it's 0. Okay, so that's always going to be there. So anytime we have a positive z value, it's going to be to the right. Anytime we have a negative z value, it's going to be to the left. So this negative 0.19 is to the left. That's where this line comes from here. And we want to find less than, so we have it shaded to the left side. Okay. Now, I'm going to scroll down here and look at a table, and that's one of the things in the tables and formula sheet that I put in the chat right at the beginning of class. So we have this z-score table, and we have these values on the outside. Okay, we have the z values here going down the first column and across the first row. Okay, those are what we're going to look for to find our particular z value. So if we notice up here in the corner, we have this pretty picture of a normal distribution. Notice that that shaded area is to the left of whatever z value that we're given. Okay, this table always gives us area to the left, always gives us area to the left, always gives us area to the left. Okay, so anytime we look up something on the table, it's going to give us area to the left. Well, what we're looking for in this problem A is exactly what they give us. We're giving us area to the left. Okay, so we're saying less than negative 0.19. We just have to look up that negative 0.19 on the table. Okay, so let's see how we do that. All right, so along this first column, that gives us our 10th digit of our number. So these get closer and closer to 0. And if we go all the way down here to the bottom, we see that we have a negative 0.1. Okay. So we have the negative 0.1. Now, the hundredths digit, the 9 part of that number, comes from the top of this table. And it starts off 0, 0, and then 0, 1, 0, 2, 3, 4, all the way to this last one at 0.09. So we line up that column and that row. And that's where we get this number here, the 4247. So we get the negative 0.1 from our first column and the 0.09 from our first row. We line up that row, that column, and we get to 0.4247. What that's telling us is that this area and or probability to the left of negative 0.19 is equal to 4247, and that's our answer. Okay. So not too bad. Any questions on that one before I go to the next one? Okay, so we'll do a few of these by the table, and then I'll introduce StatCrunch to show you how StatCrunch can help on this. All right, so let's see what happens with part B. Same idea, but now we're trying to find the probability of less than 2.01. So the only thing that's changed is now we have, instead of a negative number, we have a positive number. We have 2.01, which is going to be to the right of 0. And we're still trying to find the area to the left. So we're trying to find everything less than that. The only difference is when we go to our table, we don't want to go to our negative z-scores. We go down to the second part of the table, which is the positive z-scores. We line up the 2.0, which is, let's see if I can fit all this in one. Okay, I can fit all this barely. Okay, so we got the 0.20 here, and we have the 0.01 here. We line up that row, that column, we get the 9778. So the same thing, we just use the positive side of the table versus the negative side of the table. And that's where the 9778 comes for part B. All right, now I'm going to talk through this part C and see what changes here. The difference here is that we're looking for greater than 1.82. So we have the 1.82 here. If we look that up on the table, just as we've done the other ones, that's going to give us the area to the left, which is, from the table, is going to be 9656. That's great and all, but we're not interested in the area to the left. We're interested in the area to the right. So the way we have to manipulate that is we know the total area under the curve is 1. If we know the area to the left is 9656, we find the difference in those two numbers, like we did here, 1 minus and 9656, what's left over would have to be what's to the right. So the right would be the 0344. So whatever the area is to the right and the left have to total 1. Now, notice that I've sketched these first few problems, and, sketched a little graph and, looked at the area to the left or the right, whatever we may be looking for. I highly recommend that you spend the, few seconds to sketch out what you're looking for, especially for something like C. Because what can easily happen, you say, okay, 1.82, you look that up on the table or use StatCrunch, you get this 9656 and you type that in and you're confident that you got it right because it's just like the previous one and you're ready to go. But it's not the 9656. We're looking for the area to the right. You gave the area to the left. And that's where the mistakes occur in this chapter. Okay, so make sure you know what you're looking for. Are you looking for the area to the right or left? And the best way of doing that is just sketch it out so that you know what's happening. Okay. All right, I'm gonna talk through this part D, and then I'm gonna go through StatCrunch on showing you how to do each one of these in StatCrunch. All right, so this one, we're looking between negative 1.96 and 1.96. So we're trying to find the value between these two. So we're looking for this red area. Okay. Now, we have to figure out how to do this without causing too much problems. So if we look up the 1.96 in our table, that always gives us area to the left. So that's going to give us from here all the way left. Okay, that's where the 975 comes from. We don't want all that area. We want to eliminate that lower portion. So if we look up negative 1.96, that's going to give us from there to the left, okay, which is the 0.250. So if we want to get that red area, we need to take the blue area minus the green area, and we'll be left with the red area. Does that make sense of what I'm saying that? How that works? Questions? Okay. I'm going to redo all these problems with StatCrunch so we get familiar with how StatCrunch can help us with this. And so let me see if we can get this going here. All right, so we're going to go, I'm going to try to see if I can fit all this on one spot here. All right. Where we're going to go is under Stat, Calculators, and Normal. Okay, so Stat, Calculators, and Normal. So then we have this normal calculator. So what we have here is we already have the mean of 0 and standard deviation 1. Since we're dealing with standard normal, that's exactly what we want. So we don't want to change that one bit. Okay. All we have to do is enter in the value that we're looking for. So in part A, we're looking for less than negative 0.19. In this middle bottom box, we can put in that negative 0.19 and hit compute. So what we've just done there is that we've entered this 0.19. That's our breakpoint right here. Okay. And what they've given us is this 4246 or 4247, and that's the area of this red region. Okay, so it's doing what the table is doing in a more efficient way. So remember, this number in this middle bottom box are giving our outside value, and the bottom right is giving us the inside or the red value. So let's see how that changes for the second. The second, we're looking for less than 2.01. So we just have to change this to 2.01. And again, the 2.01, for some reason my pen is not working. The 2.01 is this breakpoint. The 9778 is the area of the red region. For some reason my pen is not working, but okay. We'll just leave it as is. All right, so that 9778 is that area of the red region. All right, any questions on either one of those? Okay. Now let's see how things change with 1.82, greater than 1.82. Let's see. I've got a question here. Let's see what it says. My computer's a little locked up, so okay. Oh yeah, it's so you're going to go under Stat and Calculators. Thank you for answering that before I got to read it. Appreciate it. You guys are great tonight. My computer's not working very good. My internet's not working very good, but you guys are doing great. So far, every question you guys have helped out with testing centers and helping with the course. So yeah, this is great. Okay. So yeah, so let me show you how to get on there just to make sure everybody's on board. So we go under Stat, Calculators, and Normal. Okay, so Stat, Calculators, Normal. All right. So let's see how this changes with this last one. Or this, not the last one. Part C is greater than 1.82. This is where you have to be careful. So if you put in 1.82, you're like, okay, great, I'm ready to go. But notice that the lower portion of it is shaded. We don't want the upper, the lower, we want the upper. So we're looking for greater than 1.82. This is where StatCrunch can be very helpful because they allow us to change this from upper to lower or lower to upper, whichever way you're going. So there's a little choice there between less than or equal to or greater than equal to. So if we flip that, we can find above 1.82. And with the table, we're not able to do that. We always have to manipulate it in some way. So again, this 1.82 is our breakpoint. The 0.0344 is the area of the red region. Okay. Part D, where we're going between negative 1.96 and 1.96. This is really, really nice on StatCrunch. StatCrunch has this option of between up here at the top. We've been doing standard. We go between, that allows us to put it between two values. Okay. So going back to the empirical rule from a few chapters ago, we had within one standard deviation was approximately 68, within two is approximately 95, and within three was 99.7. Notice that default here is between one standard deviation. Okay, it's one below to one above, and that's approximately 68. That's where we were getting that value. Okay. If we were doing two, -2 to 2, that's our approximately 95%. Okay, that's where we're getting that approximately 95 from before. Okay. What we're doing here in this problem is going from -1.96 to +1.96. Okay, that is very, very close to 95%. That's much more accurate than what we were doing before. So the 2 that we were using before is actually 1.96. That's closer to 95% than actually 2 is. Okay, so this is our true 95%. Okay, so it's not 2 standard deviations, it's 1.96 in either direction. That gives us 95%. Okay. You're going to see this 1.96 a bunch of different times. That's going to be, kind of a common one that we run into. And then part E, we haven't done this one before. This is greater than -3.8. We only have one value there, so we can go back to standard. If we put the -3.80, we want to find greater than that, so it's greater than or equal to, and that's pretty much everything. Because 3.8 is off the chart to the left, and everything above that. So the probability that occurs is quite high, 0.9999. Okay, so that's pretty much everything. Okay. All right, so let me stop there for a second, make sure everybody's comfortable. Do we have any questions on those or how StatCrunch works? Or we need to look at a few more of those? Everybody comfortable? Okay, I'm not hearing anything, so that's hopefully a good sign. All right, so let's see how this next set of problems changes things. All right, so assume standard normal distribution. So let's remind ourselves what standard normal means. So standard means a mean of 0, standard deviation of 1. Okay, so the same as what we've been doing. But now we're supposed to be finding the 90th percentile. Okay, so let's see what we're talking about when we find this. So far, what we've been doing, let's see what this chat says, 1 second. Yes, exactly. So Caleb's asking on StatCrunch, can you change it to calculate greater than? Yes, and that's one of the awesome things about it is say we're trying to find, I think you said 1.8. So greater than 1.8, we can just find greater than 1.8 just like that. And if they want us to find less than 1.8, we can find less than 1.8. That's what's so great about this versus using the table, because the table only gives us to the left. So here we can just switch, from left to right, just a matter of changing it from less than to greater than. Okay. Yeah. So Caleb, if you once you start getting familiar with it, and all of you guys, once you start getting familiar with it, it should be okay. Now realize that we're going to take the test, and I don't imagine anybody's going to look at chapter 6 until after the test. So it's going to be a week or so before you look back at this, and you're going to forget about it, how to do it, and all that. Let that panic kind of settle down and work with it a little bit. Send me an email, and I'll help you out. Remembering how to do all this. But yes, StatCrunch can be very helpful in this. Okay, so in this particular one, we're looking for the 90th percentile. All the other ones we've done so far, they've been given this outside value, whatever the Z value was. Like one of them we had was 2.01. I remember that one is, and we're trying to find above or below that. Okay, we've been given the outside value, and we've been finding the area or the probability, which is the inside. Now what we're doing is just the opposite. We're given the inside value and we have to find the outside. Okay. So let's pull up StatCrunch and see how that changes. Okay. So for instance, let's just use this example of the 1.8. The 1.8, what that is telling us, the 1.8 is just our cutoff value for here, the outside value. The 964 is the area of this red region. Okay. Now what we're looking for is what Z value does 90% fall below. So we want this red area here to be 90%. Okay. So what when instead of entering the 1.8 in or whatever we have, we use this lower right box and we enter in what we're looking for. We want to define, oops, we wanted to find that lower piece to be 90%. So what we just did is we said, okay, we need to be 90%. We wanted to find this to be 90%. And then we're saying, all right, well, if we want that to be 90%, where does this cutoff occur? And that cutoff occurs at 1.28. Okay, so we're doing the same thing as what we did before, but instead of going from A to B, we're going from B to A. We're just reversing it. Okay. Questions on that? And let's look at critical value. So critical value is a similar type thing. Okay, good. And we have a Z of 0.025. What that means is that we want to find what Z value. Okay, so we're figuring out where is this cutoff so that 0.025 falls above. Okay, so we want the 0.025 in the upper piece. Okay. All right, so we just have to define that. Now they're giving us the inside or the area. So let's see how StatCrunch can help us there. So we want 0.025. So if I enter in 0.025, the problem with that is that's the lower bound of it. I don't want the lower bound. I want the upper bound to be 0.025. So I need to switch that around. Enter in 0.025 in the upper piece. Okay, again, this is why you want to sketch what you're looking for so that your pretty picture that you sketch and your pretty picture in my StatLab or in StatCrunch match. As long as they match, you're all set. So again, what we did is we said, okay, we want 0.025 in this upper piece. So we define that upper piece, that red area to be 0.025. And we're looking for what is this cutoff here? And that cutoff is the 1.96. Okay. All right, so let's look at the second one. Same idea, but now our critical value is 0.03. Okay. So we want 0.03 in this upper tail. So again, what we're looking for is we want the 0.03 in the upper tail, so 0.03 in here. We're saying, okay, where is this cutoff value? Okay, so we're defining the inside value and trying to figure out what the outside value would be. So we want that upper tail to be 0.03. So I put the 0.03 in this lower right box. I want it, notice I have it greater than or equal to, which will put it in the right side. Our pretty pictures match. We have the red area at 0.03 and our cutoff is at 1.88, which is what we found here. All right. Okay, so now what we're going to do is we're going to look what we just looked at is standard normal distribution, and remember standard normal means mean of 0, standard deviation of 1. Now what we're doing is we're talking about just a normal distribution in general. So that not necessarily a mean of 0, standard deviation 1. It can be any mean and any standard deviation. Okay? And we have these two formulas, the z-score and then finding values from known areas. I'm going to pull those back out when we need those, when it makes more sense. So let's move on, and then I'll come back to those formulas when we need what they're helpful for. Okay. All right, so what's changed here is it says IQ scores are normally distributed, doesn't say anything about standard, with a mean of 100, standard deviation of 15. So we are dealing with a different mean and a different standard deviation than what we were before. That's all we're changing. Okay? So let's see how that changes the problem and how that helps us, or not helps us, but how that changes things for us. Okay, so here we're trying to find the probability that X is above 91. Okay, so we have the probability of X is equal to 90, greater than 91. Our mean is 100, so our mean is right down the center at 100. Okay, so the 91 would be to the left of it. This is our 91 here. And we're trying to find area above it. Okay, so very similar to what we did before, but now we have a different mean, a bit different standard deviation. A couple things I want you to pay attention to. Notice I'm using X here. What I was using before was Z. The Z represents the standard normal, meaning a mean of 0, standard deviation of 1. X means it's not standard normal, some other standard deviation, like in this case 100 and a standard deviation of 15. So I've changed variables because all that says is we're no longer doing standard normal. Now this is where we run into a couple options. Now our table, if we decide to do it by a table, that's based on 0, 1, mean of 0, standard deviation of 1. If we wanted to try to do this by a table, we would have to have a table for every mean and every standard deviation there is. So that would be an infinite number of tables. We don't want to carry around an infinite number of tables, so that's not an option. Okay. Now, here we go back to that formula that we skipped over, and we see why that's useful. Okay. Now, this formula is going to take this X, 91, and what it's going to do is going to convert it into a Z. And the way that happens is we take our X score, which is a 91, we subtract the mean, which is 100, and divide by the standard deviation of 15. What that does is takes the X score and changes it to a Z score. Okay. So we calculate that and it comes out negative 0.6. So whether we say X is greater than 91 or Z is greater than negative 0.6, it's the same probability. So once we've gotten to the point where Z is greater than negative 0.6, then we can do it exactly the same as what we did previously. So all we've entered is this new step where, okay, we have to change it to 0, 1, or standard normal, so that we can use our table. So if you're going to do it by the table, you'd have to use that conversion every time. Now, luckily, we have our lovely StatCrunch, and let's see how that changes. Notice here that I have this breakpoint. That breakpoint is at X at 91 or Z at negative 0.6, just like we have here. Now, if we do this on StatCrunch, StatCrunch can handle any mean, any standard deviation that it gives you. You can give it. So in this case, our mean was 100, standard deviation of 15. So we can put in the mean of 100, standard deviation of 15, and we're trying to find the probability of above 91. So we just give the same values that they gave us. Mean is 100, standard deviation 15. We're looking for above 91. Make sure our picture matches. Yep, we're trying to find the area to the right. We have the area to the right. Everything's great. And we immediately get the 7257, which is the answer. Okay. So StatCrunch is lovely. As long as you give it what you're looking for and make sure your picture matches what you're looking for, it does it all for you. It's wonderful. All right, so let's see how that changes with this number 7. It's number 7, we're still dealing with the same mean and same standard deviation, but now they want us to find the probability between 79 and 133. So they're giving us 2 values, and we want to find the area between them. Okay, so all this mess here in the middle. Okay. So to do that by hand, we would have to convert both of them to Z. Okay, so I converted the first one to Z. Okay. And I also convert the second one to Z. And we'd have to, look up both those values on the table, subtract one from the other. It's kind of a long process. Okay. Now let's see what happens with StatCrunch. Since we have two values, we can go to between. And we have our lower bound, which is 79. Our upper bound, which is 133. Okay, so we have the same mean, same standard deviation. We just have to enter those two bounds. It just looks like our pretty picture as well. We have the two bounds. We're looking for that red area in between, which is 0.9053. All right, how are we doing so far? So far, so good? Okay, so no comments. So I think that probably is a good thing. All right, now.
Wait, can you go over the last one and putting it into StatCrunch again real quick for that one?
Sure. Sure. Okay, so let's go back to the previous one. So I'm redoing it all. Since there's two values, the 79 and the 133, we're trying to find the area between those two. I'm going to go between. I still enter that mean of 100, standard deviation of 15. And then I enter our two values that are given us, the 79 to 133. So I enter those two, which will give us those two cutoffs. So that 79 is this lower cutoff. The 133 is the upper cutoff. And we're trying to find that area between these two. And that's the 90.53%. Okay. Does that help?
Yeah, that's good. I appreciate it.
Okay, no worries. All right. Now this one is similar to the problem we worked before. Here we have still our IQ scores with a mean of 100, standard deviation of 15. Now we're looking for the 90th percentile. So we're looking for what IQ score does 90% fall below and 10% above. So we looked at this previously, and we had the 90th percentile. We're looking for, okay, what cutoff separates the lower 90 from the upper 10%? And we found the Z value to be 1.28. Okay, we did that previously. I want to do that again just to make sure we all remember how to do that. This is standard. If we had a mean of 0, standard deviation 1, and we want that lower piece to be 90%, that gives us the Z value of 1.28. Yes, whoever wrote that, yes, we don't have to calculate the Z with StatCrunch exactly, which is lovely. Okay, so StatCrunch will do all this for you as long as you give it what you need, and your picture matches. You're in good shape. Okay, and it'll take a few times, get practice, make sure you're dealing with the inside and the outside and all that kind of stuff. But once you get rolling, it should be very nice. Okay, so if we had a standard normal, meaning Z, we have the mean of 0, standard deviation 1. We want that lower piece, the red area, to be 90%. That gives us this Z value of 1.28. That's where this Z value here comes from. Now, what that means is that the 90th percentile on Z-score is 1.28 standard deviations above the mean. Now, we don't want to know how many standard deviations above the mean. We want the actual score. And that's what this formula is for. Okay, this goes back to an X score, which is in this case, a IQ score. So what we have is, I'm going to underline these in sequence. We have 1.28 standard deviations above the mean. Okay, so let me do that again. What that formula is doing is converting it to an X score. And again, it's 1.28 standard deviations, which is the 15, above, which is the plus, the mean, which is 100. So all we're doing is going 1.28 standard deviations above the mean. So 1.28 times 15 plus 100 gives us the ISQ score of 119. Now let's go back to StatCrunch and let StatCrunch do all this for us. We have our mean of 100, our standard deviation of 15, and what we're interested in is that lower bound being 90%. Okay, so what we just defined is we want the lower piece here to be 90%, and we're saying, where is this cutoff? Right here, and that cutoff is the 119.2 as we found on my notes as well. Okay, so again, once you get the mean, the standard deviation, what you're looking for on that bottom row, it'll give you the other one. Whether you're looking for the inside or the outside, they'll just enter in the one that you enter in all three that you have, and it'll give you the third one. Okay. Again, make sure you sketch it so you're not looking to the left when you're supposed to look to the right, or vice versa. Okay. All right. Now this one is this is kind of a good overview problem. It's kind of silly too, but it gives you going both directions. So when I'm going through this, make sure you understand why I'm doing things. If not, speak up so that we know. Okay, so this one kind of encompasses everything all at once. All right, so it says the length of pregnancies are normally treated with a mean of 268 days. So we've changed our mean and standard deviation, and a standard deviation of 15 days. In a letter to Dear Abby, a wife claimed to have given birth 308 days after a brief visit from her husband who is working in another country. Find the probability of pregnancy lasting 308 days or longer. What did the results suggest? Okay, so we're testing this pregnancy length. All right, so her husband's been away for 308 days, and the wife is about to have a baby, and we're trying to figure out the probability that this is the husband's child. We know that the average length of pregnancy is 268 days with a standard deviation of 15, and this birth is gone 308 days. So we say, okay, what's the probability that it's the husband's child? Okay. So we're looking for the upper bound. Okay, so above 308. So we have to enter in our mean of 268 days, standard deviation of 15, and we want to find above 308 days. Okay, careful, I went below there. Okay, make sure you go above. We wanted that upper bound. So the probability that that baby is the husband's is 0.0038. So pretty low. So we could probably conclude that the wife has had a little extracurricular activity while the husband was gone. So yeah, poor guy, exactly. Okay. All right. So that's that we were given. Notice that we were given the outside number of the 308, and what we're looking for is this probability, which was very, very low. Okay. Now this part B is working in the opposite direction. It says if we stipulated a baby is premature if the duration of pregnancy is in the lowest 3%, notice that they're now giving us a lower bound of 3%. Find the duration that separates the premature babies from those that are not premature. Okay, so now what they're defining is they're giving us this area, and we're looking for the outside value. How many days would that be? Okay, so we still have the same mean and standard deviation, but now we have to enter in that lower right box the 0.03. So we're defining the red area. We're defining the red area, and we're looking for where this cutoff is, and where that cutoff is the 239.7 days. Okay, so it's going both directions. Okay, so the first time they gave us the outside number of 308 days, and we're looking for the area. In the second part, they were giving us area, and we're looking for where the cutoff is. So we can go from A to B or B to A. So you got to just be careful what you're looking for. All right, I'm going to hesitate there for a second. Does everybody understand how that works, and any questions on that? Can I explain the last part again? Yes. Okay, so the last part, what they're looking for says if we stipulate that a baby is premature during the if the duration of pregnancy is in the lowest 3%. So they're giving us the inside value. So in other words, they're giving us this area. They're not giving us the outside value. They're giving us inside. So when I entered that, I had to put in the 0.03 here, which designates this red area. So we're saying, okay, if you're in that red area, that you're considered premature, but if you make it past this cutoff, you're not considered premature anymore. And when is that cutoff in terms of days? And that's the 239.7 days. Does that make sense? Okay, good. All right, now this last section is called the essential limit theorem. So we're going to spend a little time explaining what the essential limit theorem is, and then how it's used and why it's useful for us. Okay. Just as a kind of a start off here, to be able to use the essential limit theorem, the original distribution has to be normally distributed or the sample size greater than 30. Okay. I'm going to explain why that is the case, and then we'll spend some time with it. All right. So we have this essential limit theorem diagram here. So let me try to explain what we're doing here. So let's just look at this uniform distribution column and see what's happening there. Okay. Say we're sampling of size 30. So what that means is we're taking this first distribution, this uniform distribution, and we're selecting 30 values out of that uniform distribution. So we find those 30 values, and we find the mean of those 30 values. Okay, so we find the mean of the first sample, and whatever that comes out to be, we have a mean. Then we go to that uniform distribution again, and we sample another 30 values. We find the mean. Okay, so now we have the mean of the second group. Okay. And then we take another 30 values from that uniform distribution. We find the mean of the third group. And we keep doing that again and again and again. So we have this whole set of means. Now, if we look at all these means and we build a distribution around those means, like a histogram or dot plot or whatever it may be, if we build the distribution of that, that's going to look like this bottom distribution. Okay. Now, why is that significant? Because we started off with a uniform distribution, and now we have something that's normally distributed. Okay. The normal distribution we know everything about. That's what we've been doing. That's what our little StatCrunch program does. That's what our table does. We can find probabilities of anything we want in a normal distribution. So we know all the properties. We know all the tricks. We can work with normal distribution all we want and be very happy. But if we have some distribution that's not normal, say a skewed or random distribution like these last two, we don't know a lot about those. And making inferences about those type distributions is very hard. But notice, it doesn't matter if it's a uniform distribution, a skewed, a random, as long as we sample 30 from it, like we did before, they all become normally distributed. Okay. In other words, these values, these 6 blocks here, let's clean this up a little bit. These 6 blocks here, we don't know much about, and making inferences about distributions like that is going to be hard. If it's normally distributed, we know everything about it. And all these are normally distributed, and we can do that. To be normally distributed, one of two things has to happen. It's got to be normally distributed to begin with. So if it's normal to begin with, it's always normal. Okay. If it's not normal, like one of these other uniform, skewed, or random, we have to sample at least 30 for it to become normal, which is this row. So going back to those two conditions, the original distribution has to be normally distributed to use the central limit theorem, or the sample size is greater than 30. So all that means is that you're in one of these categories, so one of those L shapes. It's got to be normally distributed before we can do anything with it. Okay. So what it does is take these crazy variables or these crazy distributions, and if we do the sample size of the means, or not the sample size of the means, sorry, the distribution of the means, it becomes normal, and then we can do all kinds of stuff with it. So it takes a distribution we can't do anything with and changes it into a distribution that we can do something with. Okay, which is very helpful. Now, a couple properties here. Notice that in the uniform distribution, the mean is going to be right down the center. When we sample 10, the mean is still right down the center, and it remains right down the center. The mean always remains the same, even if we, as we take those sample means, we take a sample size of 30 and find the mean of the first group. The sample size, we take a sample size of 30 and find the mean of a second group, and we continue to do that. The mean of all those means is going to be exactly the same. The mean doesn't change, is what I'm saying. Now notice as we go down, the width of our distribution is shrinking. It's getting skinnier. Okay, so as we go, like look at this random row, it's a pretty fat distribution, gets a little skinnier, and then a little more skinny. As it goes down, as n increases, it gets sucked in a little bit. So the standard deviation changes. The standard deviation is now the standard deviation that we started with over the square root of n. So in this case, it would be 30. All right. So I realize that all that is a little confusing. Let's figure out how that applies to what we're trying to do and why this changes things. We have a new conversion. If we're talking about a mean, we do the same similar conversion like we did in the previous section, but now we take the mean minus the sample mean minus the population mean, and we divide by the new standard deviation. Okay, so the old standard deviation over the square root of n. So we have a new conversion. Right. So now that I've got you guys getting confused, we're going to do a problem, and we're going to compare the difference between the two and see how things change, and hopefully, hopefully get back to where we need to be. Okay. All right, so let's see what we got here. Assume that females have pulse rates are normally true with a mean of 74 beats per minute and a standard deviation of 12.5. Okay, so we have a new mean and a new standard deviation. Okay. And then we're going to look at part A. It says if one adult female is randomly selected, find the probability that her pulse rate is less than 80 beats per minute. Okay. This is exactly what we did in the previous section. We have our mean, our standard deviation, and we're trying to find the probability of a single female has a pulse rate of less than 80 beats per minute. Okay. If we're going to try to do it by hand, we can convert it to a Z and use the table by using this formula. Okay. Let's see. Okay, so Caleb is not happy with me. He said I lost him. Caleb, give me about 3 or 4 minutes and see if I get you back, okay? So this is exactly what we did in the previous section. So let's just remind ourselves how to do that. So we have our mean in this case was 74. Our standard deviation was 12.5, and we're trying to find the probability of less than 80 beats per minute. Okay, so here's our 80 cutoff. Okay, so we define that 80 to be our cutoff. We want to find the probability of less than, which is the left. The probability of that occurring is the 68.43%. So nothing different than what we did in the previous section. Now let's see how that changes with part B. So part B, it says if 16 adult females are randomly selected, find the probability to have pulse rates with a mean less than 80 beats per minute. All right, so I'm going to go back and read both of these with emphasis so we can tell the difference. All right, A, it says if one adult female is randomly selected, find the probability that her pulse rate is less than 80 beats per minute. We're just talking about a single female. Okay, so that's the what we did in the previous section, and we're just talking about one. Now let's look at B again. It says if 16 adult females are randomly selected, find the probability that have pulse rates with a mean less than 80 beats per minute. So now we're talking about the 16 women together having a mean less than 80 beats per minute. That's where the central limit theorem comes into play. Okay. So what happens, notice here I've written the probability that X bar is less than 80. So before I wrote the probability that X is less than 80. We're just talking about a single female. So if we're talking about a single female, we would have to use this conversion. When we're talking about a mean of females, which we are now, we'd have to use a new conversion. In other words, the new standard deviation. Now, this is where we got to be careful. We have our mean of 74. Okay, we're looking for less than 80. But what's incorrect here is our standard deviation. Our standard deviation has changed. It's no longer 12.5. It's 12.5 over the square root of n. So it's 12.5 over the square root of 16, because we have 16 females that we're interested in here. Okay. So what happens is this 12.5 has to be changed. That's the new one is 12.5 over the square root of 16. So the square root of 16 is 4, so 12.5 divided by 4 turns out to be 3.125. We have to change the standard deviation. Once we change the standard deviation, we're going to have a drastically different result. Okay. So as soon as we see we're talking about a mean, that introduces a new standard deviation. So the new standard deviation is the old standard deviation over square root of 16 in this case, whatever your sample size is. Okay. Okay, so does that answer your question? I was actually answering your question as you typed it out. So as soon as we have a mean, now our standard deviation changes. So in other words, going back to the picture that Caleb likes so much, as we go down this list, our standard deviation changes. It goes down and down and down. It goes down by the square root of n. So here we have the standard deviation of sigma. Here we have the standard deviation of sigma over the square root of 10, because we took 10 samples there. Okay, and then here we have the standard deviation over the square root of 30, because here we have 30 samples. It changes as we change our sample size. Okay, so we have to manually change that. And we know that because we're talking about a mean. As soon as we talk about a mean, we have to use a new standard deviation calculation. Okay, does that make sense, everybody? Any questions on that? All right, and then this last question says, why can the normal distribution be used in part B even though sample size does not exceed 30? Okay, so we talked about, we need, sample size of 30, and then we had a sample size of 16, and we went ahead and did it anyways. The reason why we're able to do that is we have one of two possible things. It can be greater than 30, or the original distribution can be normal. So if we look carefully at our directions, what it says is assume females have pulse rates that are normally distributed. As soon as we say it's normally distributed, we don't care the sample size because we're already in this first column because it's normally distributed. We don't care about the size of the sample. If it did not say it was normally distributed, then we'd have to have at least 30 to continue. Okay. Does that make sense to everybody? All right. Let me stop there and see if you guys have any questions. Okay. So that's chapter 6. I think as you start rolling with it, it'll start coming about. The first few are going to be hard, and then all of a sudden it's going to start clicking, and it should be okay. Remember that if you don't look at this for another a week or week and a half after the test, it's going to be a little daunting. Certainly send an email if you get stuck or get in touch with me. We can set up another WebEx, whatever it may be. Okay. So the very first question, yes, because we had connection issues. Sure. Let me see if I can share that again. All right, let's see what we got here. All right, so what we had is we're talking about the uniform distribution. So let me quickly do that again. So what we said is uniform distribution is anything is likely, any number is equally likely between, in this case, 0 and 10. So we force that to have an area of 1 by adjusting the height. So if their width is 10, our height has to be 1/10 so that the total area is 1. So that's always going to be the case for uniform. So if the width was 20, the height has to be 1/20. If the width was 5, height has to be 1/5. So when we look at this next one, it says we have uniform wait times between 0 and 5 minutes. So our width is 5, our height has to be 1/5. So when we say get to this problem number 3, it says find the probability of greater than 3 minutes. What we need to do is we need to find the area of this shaded region because the area equals the probability. Okay. So if we find the area of the shaded region, we go from 3 to 5. That width is 2. Our height is 1/5. So we multiply by the height of 1/5. 2 times 1/5 is 2/5 or 40%. So the area is 0.40 and the probability is 0.40. And that's the whole key. Okay. Let's see if that helps. Okay. Is that good? Okay. Yes. So yeah, there'll be just a couple questions for the uniform. Yes. And it'll be done just like that one we just did. But there's just a couple there of those. It's not heavily tested on or anything like that. Just kind of give the idea that the area and the probability are both the same. Okay. So I think everybody heard this, but I'm gonna not have a lecture next week. I just want you guys to concentrate on the test. So I'm gonna cancel next week's lecture, and then let you guys take the test, and we'll come back and start chapter 7 in 2 weeks. Chapter 6 is not due for 2 weeks, so you have some time on that. You can focus on the test, and then look at chapter 6 after that. The test is only through chapters 1 through 5. Okay. Any questions as far as how to get there on the test or what's allowed on the test or anything like that? Do I know how the online proctoring works at all? I haven't had very many issues, but what you do is when you're ready, you go to the Canvas shell and under Smarter Proctoring, and you just click on there, and I assume they ask you a couple questions, and then they're going to enter in the password and say, go ahead and start taking the test, and you have 2 hours to do it. But that's pretty much all I know about it, Kel, because I've never actually taken a test using it. But it seems like pretty much how it works. Okay. All right, anybody else? Okay. If you guys feel comfortable, you go ahead and drop off, and I'll see you in 2 weeks. If you certainly have any questions on the how the test works or the practice test, please get in touch with me. I'll gladly help with any of that. The stack crunch should be just like on the quiz. It'll be accessed on every single problem on the test, just like everything else. So it shouldn't be a separate browser. It should be part of the test, just as the quiz and the homework. Okay, any other questions?
I had one from chapter 5.
Okay.
Let me pull it up. Because I was doing that one earlier today. Written down, I'll show you. I'm sure
I'm gonna
you
go ahead and
end
stop
up-
the recording here just because it's a
Yeah, that's fine.
individual. Okay.
Sorry,